afternoon. I'm the speaker Zhiyu and really welcome you guys to my session. So my topic is called Delta Tensor. So here's our team. My teammate Liao Liao and Liam, they are sitting in the first row and they will join the Q&A session. So we are all students from Northeastern University and we have work experience in the database management in the cloud. So that draws our interest in the tensor storage, and that's where this project came in. So the contents will be divided into 6 sessions. So first, let's do a bit introduction of our background. So we all know that currently we are in the era of the foundation models, and the large language models like Llama and GPT, they possess billions of parameters. But actually, currently, there are no efficient methods for the tensor storage. The methods, they either take redundant storage space or the processing speed will be low, like the Python loader. Also, we noticed that for the current work, they more focus on the vector, which is just 1D array, rather than focusing on the tensor storage. Also, we noticed that some of them just overlook the storage on cloud, which actually offers more advantage than just disks. So here comes the objective of our project, which is to find out a way to store the tensor efficiently in the cloud object storage. So currently, people actually will store the PyTorch PT format for the tensor. But here comes the questions. So as you may know, PyTorch is a computing framework. They focus more on the in-memory operations rather than store it on disks. So people using the PT format to store the tensor actually will have redundant storage space. So to illustrate this problem, we have some methods that can optimize the storage, and we utilize the Delta Lake as the underlying framework. So Delta Lake can offer us some optimization techniques in the storage, and we can use them. And here are some terminologies. On the left-hand side are just some definitions of vector and tensors, and also the process to encode and decode the tensor. On the right-hand side are some evaluation metrics that can evaluate our performance in our project. Like the compression ratio is just to measure our space efficiency in storing the tensor, and the writing and reading time just to measure the time efficiency in processing the tensor. And we have in total 3 methods for the tensor storage. For the general tensor part, so we actually divide the tensor into both general and sparse case. For general tensors, our method is called flattened tensor storage format, FTSF. So you may notice that on the left-hand side, there are actually a 4D tensor. And the way FTSF to encode it is to actually flatten the high dimension tensors into low dimension and then divide them into chunks. So for the 4D tensors, after we flatten it, we can got the tensor on the right-hand side. Like for the right top, it is just the 3D subtensors. And on the right bottom is the 2D subtensors. So we will store every chunk of them into a row in the Delta Lake and also together with its metadata. So this format also supports the tensor slicing operation, which means that to read a part of the tensor, and it also meets with the tenet that we only fetch the elements we need. So since we already have methods for the general tensors, why still the sparse tensor matters? This is because of the curse of dimensionality. So as the dimension of vector increase, the data sparsity actually grows, and also the data set of the tensor will be really large. When we look at the example below for the Amazon reviews, its size could be up to hundreds of thousands of petabytes, which is actually not realistic to store it directly. However, when we notice that for the sparse COO size, which is just a sparse format to store it, its size is greatly reduced to 55 gigabytes. So actually, to store the sparse tensor, we will first utilize the COO. Then just a brief introduction of the COO coordinate format. So actually, we will use COO to represent the high-level tensor into a 2D array, as you can see on the right-hand side. So we actually will represent every non-zero element of the tensor. So we will represent its coordinates and also values. And actually, we can also store this COO format into Delta Lake. So we will store every non-zero element into a row with the non-zero values and also indices. So we can see that the idea of the COO is actually straightforward, but actually it's not good enough considering its efficiency, both time and space. So next, I will introduce more methods to optimize it. So as I've said, we will first encode a sparse tensor with COO formats, but then there are two strategies to optimize. The first one is encode this COO into separate arrays, and then do the partitioning. Partition these arrays into smaller chunks. Also, the second strategy is to partition this COO directly and then apply the sparse encoding to each chunk. So our method for the first strategy is called compressed sparse fiber, CSF. So to illustrate this, we can look at an example of a 3D array, a 3D tensor. And on the left-hand side is just the COO format of this. We can notice that there are 8 elements. And on the right-hand side is actually the chi representation of CSF. And for the example, coordinate 0, 1, 0, and value 3, both highlighted in both sides, we can notice that in CSF, actually it goes from the root node all the way down to the leaf, and also the corresponding value. So each level of this chi actually just means each dimension in the COO format. But here comes the problem. How can we represent this tree representation into the program? Our implementation is to pack it into separate arrays. There are multiple categories of arrays: slicing pointer, level indices, and also values. For the slicing pointer, you can notice that it is actually in the form of prefix sum. So when you look at the f pointer 0, you can see that the value 2, it actually means that for the red node 0, it has 2 yellow subnodes, and for the value 3, it means that for red node 0 and 1, it has in total 3 yellow subnodes in the next level. And for the level indices, it just records every index in the current level. And the values just record every non-zero values. And the last step will be store these arrays into Delta Lake. So first, we'll of course store some metadata like tensor ID. Also, for the non-truncate data, it means the array we can see on the left-hand side. We'll store this array one by one and into a row. But sometimes here will be a problem, is that the array size could be really large. So storing it directly is actually not space efficient. To deal with this problem, we offer the chunk storage, meaning for the array that is larger than a certain threshold, we will just divide it into several smaller chunks and then store each chunk into a separate row. So this is another method for the second strategy called block sparse generic storage. So again, look at the tensor example. It is a 3D tensor and it is represented in COO format. And one highlighted will be illustrated further. So the first step of BSGS is actually pick up a block shape. In our case, it is set as 1 by 2 by 1. And you can see that the block shape of these blocks with the non-zero elements are picked out on the right-hand side of the PowerPoint, which includes 3 blocks for these 5 non-zero elements. And then we have the COO coordinates, we have the block shape. We will then do some operations. We will do the division and also the modular operations to get the block indices and also element relative indices on the right-hand side. Block indices just means the indices for block, and the element relative indices just means the relative position of the element inside this block. So after that, we will just try to group the element together for the elements in the same block. So we can see that in the grouping, there are actually same block indices because they are in the same block. But we will actually remove these duplicate values and only left one copy of each block indices for each block. And then we will combine all the remaining elements together to get the block values. And for the block values on the right bottom corner, we will actually do further encoding methods on them. So to store the BSGS, we can see an internal table of the Delta Lake. So there are some columns like ID, den shape, and block shape. But for the column compression, they can actually compress the same values. So only the first row's data of these columns are saved. And also, BSGS will support tensor slicing operation, and the steps are just shown on the right-hand side. And there are some steps. The first step is to filter the table using the tensor ID. By this filtering, we can get a block shape and den shape. And then we can calculate the slice shape. And also, we will scan the block indices column to get the block values. And the last step is just use this data to construct the slice. And after talking about the methods, let's look at the experiments. For the general tensors, we will use the dataset of 5,000 images from the FFHQ dataset. And then we will load all these images into a tensor in the memory. But we will actually have two copies of this tensor. One copy will go to the S3 object as binary. And for another copy, we will actually apply FDSF format and then serialize it into the Delta Lake table. And for the performance, we will evaluate by both seeing the time to read the whole tensor or a slice of the tensor. For the sparse tensor, the process is nearly the same, except that the input dataset, we will put it as COO format first. And for the Uber pickup dataset, we will load it into memory as a PyTorch tensor. And then we will apply the further encoding methods. And one more thing to notice is that there are two kinds of COO in this setup. One is the binary COO in a PT format, and another is the Delta Lake COO, which will utilize the primitive data types in the Delta Lake. And here comes the result of our project. So first, for general tensors, we have 4 matrices to evaluate it. One is the storage size, and also the time to read or write the tensor, and the time to read part of the tensor. So we can see from the result that FDSF do great in reduce the storage size. It reduced 9% of the storage space. And for the reading part of the tensor, it does even better. We can notice that it saves 90% of the time to read part of the tensor. And for the sparse tensor, first we look at the storage size, and we can see that the methods actually save the space a lot. Especially for the CSF and BSGS, the compression rate is actually less than 7% for these two methods. And for the time to write the tensor, CSF and BSGS is also competitive. So CSF is the most efficient one. It reduces 26% of the writing time compared to the PyTorch. So for the tensor reading, CSF and BSGS still do great. And BSGS is the most efficient method. It takes 30% less time to read the entire tensor. And for reading part of the tensor, it's more efficient. It saves 56% of the time. And last comes the conclusion of this project. So we offer solutions to store the tensor in the cloud environment. And also we have some customized methods for both general and sparse tensors. And the result comes out that we have achieved remarkable space savings, especially for sparse tensors. And also our performance in processing the tensor, considering its time, is also really competitive. And that's the end of my presentation. Thank you very much for listening and coming. And if you have interested in our project or you have further questions, please feel free to contact us. And also there are a QR code which will link to our paper. And feel free to ask us if you have any questions. Both Liam and Liao Liao will join the Q&A session. Thank you very much.